Okay. I hope my screen is visible to everybody. Yes, somebody please respond.
Yes, sir.
All right. Okay. So today we will continue, and today we will see a simple problem. Last time we have taken a plane stress problem wherein we have taken only one element. Today we are going to see the plane strain problem, and probably this time we'll go for the two elements. Okay. So let me start with the problem statement. Okay. So I have, let us say, a retaining wall or maybe a dam, which is something like this. Okay. So we have a dam, something like this. Now this entire base is basically fixed over here, and it is consisting of concrete, and the value of the modulus of elasticity and Poisson's ratio are given to you. Okay. So let us say the modulus of elasticity of the material is, let us say, E. Okay, is 40, that is 40 newtons per millimeter square. Okay, so I'm just putting this in newtons per millimeter square, and the Poisson's ratio value, this I'm assuming this as 0.25. Okay, so here all the units. Okay, so for the distances I'm using millimeters, and for the loads I'm using only newtons part. Okay, so we have to analyze this, and let us say this particular structure is subjected to a triangular loading. It is something like this. Okay, so we have a triangular loading. So now how to take care of triangular loading, that we will see. First of all, we have to discretize the structure, and then we have to find out the stiffness matrix, right? And for this purpose we have to use the CST element, that is constant strain triangular elements. Okay. Now for the analysis purpose, if you remember, the first step which is used in the finite element method is the discretization of the structure. Okay, so for the purpose of discretization, I'm going to draw the same structure one more time, and here this structure I have drawn. Okay, I think I have not given the dimensions in the earlier structure. So let us say this is 100 millimeters. Okay, and this is, let us say, 1000 millimeters. Okay, so let us say this is 1 meter actually, और इसका जो height है, that also I'm assuming this as 1000 millimeters. Okay, so it's a assumed structure, not the real structure. Okay, so now for this purpose I'm going to discretize this particular structure using only two elements, in such a way that I'm going to call this as node number 1, this as node number 2, this is node number 3, and this will be your node number 4. Let us call this as element number 1, and let us call this as element number 2. Okay, so basically element number 1 will be having a connectivity from node number 1 to node number 2 to node number 3. Okay, always remember it is in the anti-clockwise direction, right? The second element will be having a connectivity, let us say, from node number 1 to node number 3 and to node number 4. Okay, so you can also start with something like node number 3 node number 4 and node number 1. This is also okay, and you can also start with node number 4 to node number 1 to node number 3. This is also okay, as long as it is anti-clockwise. You can start with any of the node, but please ensure that the nodal connectivity is in the anti-clockwise direction. Okay, now for the sake of calculation purpose, I'm going to assume this as your x-axis. Okay, and this as your y-axis. Okay, so definitely the coordinates over here, this will be 0 and 0. Okay, this will be 1000 and 0. Okay, this value will be something like 200. Okay, I think I have given 200 or 100 I have given. Let us make this 200. Okay, because 100 will be a very small value. So let us make this as 200 So if you use this, this value, the x coordinate of this particular node will be something like this, will be 200 and y will be 0, and this, the x value will be 0, y value will be 1000. Okay, here also I have made mistake. This should be 1000. Okay, because the height of the structure is 1000. Okay, I hope this is clear to everybody. Okay. So now let us start generating the stiffness matrix for each and every element. Okay. Before going for the stiffness matrix, let us quickly see what is your D matrix. Okay. So your D matrix is nothing but the stress strain matrix. And since this is a plane strain case, okay, because you see this is a retaining wall or maybe earthen dam where this third dimension, okay, so third dimension is very very large. Okay, so unlike your plane stress case where the third dimension is very small, this is a plane strain case, so the third dimension will be very very large. So we have already seen in the previous classes the derivation for the plane strain case, and it is assumed that in the plane strain case the strain in the z direction, that is in the perpendicular direction, it is assumed as 0. Okay, and based on that assumption we have already derived the expression for the D matrix. So it was something like E divided by 1 plus mu, okay, multiplied by 1 minus 2 times mu. Okay, then we have a matrix where the first element is 1 minus mu, second element is 0, sorry, mu, third element is 0, this will be mu, this will be 1 minus mu, this will be 0, this will be 0, this will be 0, and this will be 1 minus 2 times mu divided by 2. Okay, so if you refer your earlier notes, so here in the introduction chapter we have derived this expression, that is E divided by 1 plus mu, 1 minus 2 mu, then this entire matrix. Okay, so the same matrix I have written over here as a D matrix. Okay, so now we already know the values of E. So E value is 40 and your mu value is 0.25. Okay, so since we know all these values, so what I can do is I can just substitute these values in the expression so that I can get the value of D over here. Okay, so the value of D, it is coming out to be, just let me do the calculation part. Okay, you can also do the calculations along with me. Can you tell me what will be the constants which is outside the matrix? Anybody? Yes, anybody? Yes, anybody? कितना आ रहा है? बोलो बेटा, कितना आ रहा है? 64. Okay, so this is coming out to be 64. Okay, so we have a matrix D which is something like this, that is 64, and this will be 1 minus mu, so mu value is 0.25. Okay, so this will comes out to be 0.75. So you can cross check this, and this should be your D matrix, that is the stress strain matrix. Okay, now let us start with the derivation or the calculation of the stiffness matrix. Okay, stiffness matrix for element 1. Okay, so now I'm focusing only on the element 1 now. Okay, so we have element 1 which is looking like this. Okay, let me go one more time. So this is a triangular element. Okay, so I'm just drawing this element one more time. So this is your element number 1. So it is like this, and it is like this. Okay, so it has got nodal connectivity 1, this is nodal connectivity 2, and this is the third node. Okay, and here the value of coordinates are 0 0, here the value of coordinates are 1000 and 0, and here the value of coordinates x is 2200, and the value of y will be something like 1000. Okay, so what I can do is I can write the matrix, that is 2 delta matrix over here. Okay, So generally what we do write is 2 delta equals to, we have something like 1 1 1. This will be x1 y1 x2 y2 x3 and y3. Okay, so this we have seen in the previous class also. So if you write this matrix, so it will look like this one. Okay, so this is 111, and let me increase the font slightly. Let us say this is 14 and bold one. Okay, so your matrix will look like something like this. Okay, is it correct? Somebody please cross verify this. I hope this is correct. Okay, and if you take the determinant of this, okay, so if you take the determinant of this, you should be getting the twice the area of the triangle. Okay, so twice the area of the triangle, it is coming out to be something like 2 into 10 to the power 5. Okay, so this is 2 and 1
2
2
into
3 4 5. Am I right? Barabar hai beta?
sir, x2 is 1000.
Okay, sorry, my mistake. uh,
Second and third is the change.
okay, okay, just a moment, just a moment. 1
Yes,
2
sir.
and 3, I have actually Excel sheet, so I just have to put the values. So this is 1000, and I think y value is 0, isn't it? The third node is 200 and 0. Okay, I hope this is correct now. Let me correct the values. So this will be 1000, right? Okay, so this will be 1000 and this will be 200. Okay, अब बराबर है बेटा?
That's zero. Zero.
Sorry,
That's zero.
which one?
Sir, why?
Okay, yeah, this will be 0. Okay, uh, ठीक है, अब बराबर है.
X3 200.
अब ठीक है. ओके, बराबर है अभी. Okay, so now what will be the determinant of this matrix? Sorry, 1 into 10 to the power, yes, 1 into 10 to the power 6. Okay, so this will be the twice area of the triangle. Okay, so this will be required, right? Now based on this, now we can generate the value of B matrix. Okay, so if you remember, your B matrix was something like this. Okay, B is 1 upon 2 times delta. Okay, so it will be something like this, and then we have something like B1 0, B2 0, B3 0. This will be 0 C1, 0 C2, 0 C3. Okay, this will be C1 B1, C2 B2. This will be C3 and B3. बराबर है ये? Okay, so you don't have to do the calculations. I have the values available with me. Okay, so this comes out to be something like 1 into 10 to the power minus 6. Okay, into this values. Okay, so I have already Excel sheet ready with me, so that you don't have to do the calculation part. Okay, so this is just, I'm just substituting the values. Okay, and with this I'm going to get, this is your B matrix. So B matrix is nothing but your strain displacement matrix. Okay, so now we have the B matrix available with us. We also have this D matrix. Okay, so now what we can do is we can simply go for the multiplication of B into B matrix. Okay, so we have B matrix, okay, into B matrix. Okay, so if you do this calculations, if you just multiply all these values, so what you are going to get is something like 6.4 into 10 to the power minus 5 multiplied by, you should be able to get a matrix which looks something like this. Okay, so let me increase the font so that it is clearly visible. Okay, so I hope you have understood this. It's a simple matrix multiplication, not much to explain in this. Okay, so is it okay everybody? Yes, yes student. ठीक है, shall I continue? Okay. Now, similarly, we can go for the multiplication of B transpose into D into B. Okay. So we already have this B matrix over here. Okay. So here is your B matrix. Okay. And D into B is already we have calculated over here. Okay. So if you go for the multiplication directly, generally what happens is we have, or let me put it in different way. Okay, so we generally what we do is we go for k is integration over the volume, then you have B transpose into D into B over dV. Okay, so this B will be constant, it will be coming out, D will be coming out, and this B will be also coming out. Then we left with integration over the volume, that is dV. So here this will be B transpose into D into B, and here integration over the volume, now it will become integration over the area. So this will be thickness multiplied by the area. Okay, so here thickness, because this is a problem of plane strain case. Okay, so when I'm talking about plane strain case, so this will be a unit value. Okay, because the thickness is very very large, so we are calculating the stresses per unit. Okay, so if I take this as unit, so this will also come out. So as a result of this, what you are going to get, it is something like B transpose into D into B into thickness, okay, into simply area. Now where this area is nothing but your 2 delta. Okay, so remember 2 delta is the twice the area of the triangle. So your area is nothing but 2 delta divided by 2, and the thickness value. Okay, so thickness value I am taking as 1 meter, so this will be coming out to be 1000 millimeter. Okay, so as a result of this, what we have to do is just multiply these three matrices, multiply it with 1000, and multiply it with this 2 delta divided by 2. Okay, so as a result of this, finally you should be able to get the value of k. Okay, so your final k matrix, so this will be k1 matrix, that is the stiffness matrix of the first element. So I think it is coming out to be something like 0.03. So this is 0.032. Okay, so this will be a constant which is coming out. And if you do the calculations, so the values are, just let me format the values so that uh, you can get the appropriate values. Okay, so I'm just copying and pasting these values over here. Okay, okay, so just a moment, let me copy and paste these values. Yeah, so you see this will be your final k matrix. Okay, okay, have you understood this? ठीक है? Yes student, have you understood this? Please let me know. बेटा बोलो अगर नहीं समझ में आया है, आई एम रेडी टू एक्सप्लेन. Yes students, please. हार्दिक, राधिका, उन्नति, सौरभ, नयन, समझ में आया कि नहीं आया? पक्का ना? Okay, I'm going little bit fast today because I don't want to waste the time in doing calculation part. Okay, so it's just a simple matrix multiplication part, so you can please do this part. Okay, so this is how we should get the value of k1. Okay, so now let us quickly calculate the value of k2 as well. Okay, so your k2, so I'm talking about now, this will be your element number 2. Okay, so let me draw the element number 2 for you. So your element number 2 is like this. Okay, so this is node number 1. Okay, this is node number 2. Sorry, this is node number 3, not node number 2. This is node number 4. Okay, and we are assuming the connectivity as 1, then 3, and then 4. Okay, so let me write down the coordinates also over here. So the coordinates of 1 will be 0 and 0. The coordinate of 3 will be 200 into 200 and 1000, and this will be 0 and 1000. Okay, so let me put the same values in the Excel sheet also. So in the Excel sheet I have now 1, 3, and 4, and the third node is 200. Okay, and the depth is 1000, and this is 0. Okay, so accordingly, if you write down the value of 2 delta, okay, so 2 delta is something like 1 x1 y1, 1 x2 y2, 1 x3 and y3. Okay, so here this is the 2 delta matrix. So this comes out to be something like this. Someone please cross check whether this is correct or not. बराबर है क्या, चेक करो. Is it okay?
Yes, sir.
ठीक है, fine. So if you take the determinant of this matrix, okay, let me uh, draw this. So this is a simple matrix, and if you take a determinant of this matrix, so now I think it is coming out to be I think 2 into 10 to the power 4 or 2 into 10 to the power 5. Okay, so this is just 200 into 1000. That's it. Okay, so now accordingly, now we can get the value of B also. That is, B is nothing but your stress strain, oh sorry, strain displacement matrix. Okay, so for this particular element, now we should get B equals to 1 upon 2 times delta. So 1 upon 2 times delta is nothing but 2 into 10 to the power minus 5. Okay, and if you substitute the values of B1, B2, B3 and C1, C2, C3 the way we have done for K for element number 1, so you should be in a position to get the values which are something like this. Okay, so this is your B matrix. So this is your B matrix for element number 1. Okay, so you can cross check all these calculations over here. Then we can go with the D multiplied by B matrix. Okay, because this will be required. We have already calculated the value of D, and just now we have calculated the value of B for the second element. Okay, so this comes out to be something like, that comes out to 3.4. So this comes out to be 3.4 into 10 to the power minus 4. Okay, that is 1, 2, 3, and 4. Sorry, 3.2. Not 3.4. This is 3.2 into 10 to the power minus 4 multiplied by, you will have a matrix which is something like this. Okay, so I'm just increasing the font now so that you can see. Okay, so this is a multiplication of this your D matrix multiplied by your B matrix. Okay, and similarly you can go for this, that is K matrix. So directly I'm writing down the K matrix, that is integration over the volume B transpose into D into B over dV. So this comes out to be something like B transpose into D into B. Okay, into we have thickness and into you have area. Okay, so if you go for this K for the second element, so this is K2. So K2, I think it is coming out to be there is a constant which is coming out, that is 0.16. Okay, multiplied by, you will get this value. Okay, so you will be getting these values, right? So this is how you will be getting the K2 matrix. Yes. So have you understood this? Yes, students, have you understood this? K1, K2, someone please respond. Okay, fine. So now we have to assemble this. Okay, so please pay attention on the screen, because this is something different, because till now you have assembled the matrices which are having the only one connectivity, right? So let us see. So if you see K1 matrix, okay, so your K1 matrix is the stiffness matrix for nodal for element 1, which has got 1, 2 and 3 connectivity. Okay, so now if you refer this K1 matrix, okay, so in the K1 matrix you have, this is this much portion. Okay, so this much portion is for 1, okay, node 1. This much portion is for node number 2, and this much is the portion, it is for node number 3. Okay, similarly this one is for 1, okay, this one is for 2, and this one is for 3. Okay, so if I talk specifically, so this value, okay, so I can say this particular column is for 1 in x direction, this is 1 in y direction, this is 2 in x direction, this is 2 in y direction, this is 3 in x direction, and this is 3 in y direction. Similarly, this will be your 1x, this will be 1y, this will be 2x, this will be 2y, this will be 3x, and this will be 3y. Okay, so this is your K1 matrix. Similarly, if you focus on the second element, okay, so in the second element, if you see, the connectivity is 1, 3 and 4. Okay, so this much portion, okay, yeah, right, so this much portion is belonging to node number 1, this much portion is belonging to node number 3, okay, and this much is the portion, it is belonging to node number 4. Similarly, this will be 1, this will be 3, and this will be 4. So if I talk specifically, so this particular column, okay, so this is nothing but 1x, okay, this will be 1y, this will be 3x, this will be 3y, this will be 4x, okay, this will be 4x, and this will be 4y. Similarly over here, so this is 1x, 1y, 3x, 3y, 4x, okay, this will be 4x, and this will be 4y. Okay, so now what we have to do is we have to assemble this, right? So we already know how to assemble this. So what we have to do is just 1x 1x 1x, you have to put it in a global matrix, and 2x 2x, you have to put it in a global matrix. Okay, so just for sake of understanding, what I'm doing is, for the time being, I'm stopping my sharing screen. Okay, I'm just sharing my just a moment. I'm just sharing now the Excel sheet. Okay, is my Excel sheet visible to everybody? Yes, students, please confirm.
Yes, sir.
Okay. So now you see, this is the Excel sheet which I have prepared. So you see, this is your K matrix. Okay, so just now we have seen the generation of, this is K matrix, but this is your K2 matrix. Okay, this is not your K1 matrix, this is the K2 matrix. So this is a constant which is outside, and this is nothing but the matrix. Okay, so what I have done over here is I have multiplied this constant to all the elements which are over here. So as a result of this, what I have got these values. Okay, so I'm just copying this, okay, and I'm creating one more sheet over here, and let me delete the entire portion. Okay, and I'm just pasting this over here, right? Let me copy it one more time, and I'm pasting this over here. Okay, so now paste values. Okay, so now you see, what I was telling you, that this portion, okay, so this row and this column, okay, so this is belonging to element number, or sorry, the node number 1. This row, so this columns and these two rows, they are belonging to node number 3. Okay, it is not node number 2, it is node number 3. and this two columns and this two row, they are belonging to node number 4. Okay, so this is how this green color which I have shown earlier. Okay, so this second part is remaining. So what I'm going to do is I'm going to introduce two more columns over here and two more rows over here. Okay, so now what you will find, this is your row or the contribution of node 1. Okay, this will be your node 2. So node 2 is not there, so it will be blank. Okay, and this will be your node 3. Okay, and this will be your node 4. A very simple thing. Okay, so now I'm going back over here and I'm just undoing the some portion. Okay, I think I have to give the nodal coordinates one more time. So if you remember, the nodal coordinates were 1, 2, and 3. The second element x was 0, y was something like 100, sorry 1000, and this was 200, and this one. Okay, so if you see, this is what we have obtained as a 2 delta matrix, and similarly we have obtained this value constant as minus 0.16. Okay, I don't know why minus is there, it should not be minus. Okay, anyway, so as a result of this, if you multiply this over here, so you should be able to get this value. माइनस क्यों आ रहा भाई? टू डेल्टा की वैल्यू नेगेटिव नहीं आनी चाहिए ना. सेकंड कोऑर्डिनेट का x मेरा 0 है, y मेरा 1000 है. थर्ड कोऑर्डिनेट, सॉरी, आई थिंक दिस इज 1000 एंड दिस इज 0, राइट? अब ठीक है, बराबर है ना? देन बराबर है ना? ओके, नाउ दिस इज ओके, राइट? फाइन. तो ये तुम्हारा 0.032 आया था, बराबर है k1 में. यस, इट इज द सेम वैल्यू. ओके, सो आई हैव जस्ट मल्टीप्लाइड दिस 0.032 with this matrix. Okay, I think the matrix is also same, right? हाँ, तो ये मल्टीप्लाई करने के बाद जो मुझे मिला है, so it is like this. Okay, so the same matrix I am going to put over here. Okay, I'm just pasting the values. Okay, so you see, ये जो column है, okay, so this is belonging to node number 1, this is node number 2 and node number 3. तो इसमें चौथा नोड है ही नहीं. Okay, so this will be 0. Okay, so here the values will be something like 0, 0, 0. Okay, and here also we, since the second node contribution is not at all there, so this will be simply 0. That's it. Okay, so what I have done, so this is my your k2. Okay, and this is my k1. Only thing is, what I have done, that I have in place of writing it as a 3 by 3 matrix, I have written it as a 4 by 4 matrix. Okay, why I have done this? Because I have to finally assemble the k matrix. Okay, and k matrix, k global, will be the sum of this and this. Okay, so it will be something like equals to this value plus this value. Okay, so if I go for adding this, so I am ultimately going to get a 4 by 4 matrix. So this is 1, 2, 3, 4, 5, 6, 7, and 8. So I'm just basically adding this matrix and this matrix. Okay, so that I am going to get the k global matrix over here. Okay, so this is my k global matrix. Okay, I hope you have understood this. बेटा आया क्या समझ में कि नहीं आया? Okay, so this is your k global matrix. Okay, so I'm just copying this. Okay, and I'm just pasting this in the this one. Okay, so let me k global. I think my screen is still shared with the Excel sheet, isn't it? Okay.
Yes, sir.
Anyway, just give me a moment. Let me just paste these values in the. Okay. Okay, fine. Let me share the screen one more time. Okay. Let me stop presenting. Fine. And Let me share the window one more time. Okay, right. अभी दिख रहा है? Okay. So basically from that Excel sheet I have generated this K global matrix. So your K global will look something like this. Okay, but now in this particular K global what you could see is this one. Okay, so now we have, this is something like 1x, this will be 1y, this will be 2x, this will be 2y, this will be 3x, this will be 3y, 4x and 4y. Similarly, this is 1x, 1y, 2x, 2y, 3x, 3y, and this will be 4x. Okay, uh, this is 4x and this is 4y. Okay, so now what I'm going to do is I'm just quickly drawing a figure of your entire structure one more time. So it was like this, isn't it? This was node number one, this was node number two, this was node number three, and this was node number four. बराबर है? And we have discretized the structure like this. So now you see, out of this, your node number one and node number two, they are basically fixed. Okay, so since they are fixed, they are not going anywhere. So as a result of this, what I can do is I can simply cut the first line over here, because this is fixed. Okay, and the second line also I can delete, because the first node is not able to move either in x direction or in the y direction. So correspondingly, the second column is also getting deleted, right? Similarly, the second node is also fixed, so I'm just going to delete this entire portion, the second contribution in x direction as well as in the y direction. So here this will be also going. Okay, so as a result of this, what you are going to get is only this part. Okay, that is, this will be your reduced stiffness matrix, which will be having the contributions of node number 3 and node number 4. Okay, so as a result of this, what you have K reduced into delta reduce equals to force reduced. Okay, so you have a matrix which is something like this now. Okay, so let me copy this. Okay, and let me paste this. So this will be your final reduced stiffness matrix. Okay, and of course this will be multiplied with, we have the that is, let us say, u in the third direction, v in the third direction. Okay, then u in the 4 and v with the 4. Okay, multiplied by, now you have to go for the forces which are coming on the node number 3 and node number 4. Okay, so I'm just drawing one more figure in front of you. Okay, so it is something like this. So we have a wall, and on this wall we have a load which is coming like this. Okay, so for just say that this is a water. Okay, so if this is a water, so the height of the water is 1 meter, isn't it? So if it is 1 meter, so 1 meter into 10, that is the density of the water, so that comes out to be 10 kilonewton, isn't it? So this value will be something like 10 kilonewton, and this value will be 0. Okay, so if I draw the similar figure, only thing is I'm just drawing the rotated figure now. So I have a beam, okay, which is say like this, and on this beam now we have a triangular loading. Okay, so here we have 10 and here we have 0. Okay, so if you take a equivalent load, so this is this particular length. Okay, so the height over here, so this is 1 meter. ओके, तो ये भी जो है ये तुम्हारा क्या रहेगा, 1 मीटर रहेगा. ओके, सो इफ यू टेक द टोटल एरिया ऑफ द ट्राइंगल, so this will be 10 multiplied by 1 divided by 2, isn't it? So the total load of the triangular portion will be something like 5. Okay, so this equivalent load is nothing but 5 kilonewton, and it will be acting at a distance of 1 by 3. Okay, so if you take the moment of this load, so you can get the reactions. Okay, So can someone tell me what will be the reactions over here? Yes, anybody? What are the reactions? कितना आ रहा है? Am I right? Yes, students, is it correct? बराबर है क्या बेटा? Yes, anybody please respond.
सर फिर से एक बार समझिए।
फिर से बताओ, करेक्ट है ना? ठीक है, ओके।
करेक्ट है सर।
हाँ, so basically what I have done, see, we have a triangular pressure, okay? So here we have a triangular pressure like this, okay? So we have some value at the base and at the top we have zero value, okay? ये 10 कहाँ से आया? I am assuming the density of water as 10 kilonewtons per meter cube. Okay, so height of the wall is 1 meter. So the at the bottom you will have a pressure of 10 kilonewton. Okay, so I am just drawing the rotated view of this. So I have just drawn a simply supported beam which is having 1 meter length. Okay, because the height of the wall is also 1 meter, and I am just going for the triangular loading on that simply supported beam. Okay, so I am just calculating the reaction of that simply supported beam when it is subjected to a triangular load, where the value of load is continuously reducing from 10 up to 0. Okay, so based on this I have calculated the total load. So total load is coming out to be 5, and if you take out the reactions, so reactions are coming out to be 3.33 on one end and 1.67 on the other end. Okay, I hope this is pretty clear to everybody. Okay, so basically what I have done is, so there was a water pressure which was like this. Okay, so in place of applying this triangular load, now I am applying the nodal loads. Okay, so these nodal loads, they are nothing but the reactions over here. Okay, that's why I have calculated the reaction. So you see the reaction value is coming out to be 3.33 over here and 1.67 over here. Okay, so these are nothing but the reactions. So reaction usually it is exactly opposite to the loading, but since it is a representation of the load, okay, this is not the exact load, it is a representation of a load, and the UDL or the triangular load is getting converted into a nodal load. So this particular figure, okay, so this figure is very much similar to this distributed load. Okay, so now we have a load which is coming out to be 1.67, and it is acting at node number 4, that too in the x direction. Okay, there is no force in y direction, there is no force over here, and there is no force over here because there is no water pressure which is coming over here. So as a result of this, what you will get, so at node number 3 there is no force in x direction, at node number 3 there is no force in y direction, but at node number 4 we have a force of 1.67. This is in kilonewton, so I'm just putting it into 10 to the power 3. So it is like this, and as far as the y direction is concerned, it is 0. Okay, I hope this is clear to everybody now. Okay, okay, so now what we have to do is we have to solve this. Okay, is there anybody's having scientific calculator and he or she can solve this? After solving, you should get u3. Okay, you should get v3, you should get u4, you should get v4. Yes, somebody please give me the values. Yes, anybody got the answer? You can use your scientific calculator, or you can even use the standard softwares which are available with you. Even you can solve this online also, no issue. Yes, anybody? Shall I do it? Yes, anybody got the answer?
0.207.
Sorry.
Q3 0.207.
I have the answer, but
Yes, sir. 0.207.
see, I have done online. Okay. I think let me paste it over here. So this is what I am getting in the online, but this is divided by sign. Okay, this is 172. I think this is like this. Can someone tell me what is x1, please?
So
Sorry,
0.207.
wait a second. Let me write down. U3 is how much?
0.207.
0.207. Negative or positive?
Positive one.
पॉजिटिव ही आना चाहिए, because the load is from left to right, so it should be in the direction. It is in mm, right?
आपके आंसर अलग आ रहे थे.
हाँ, मेरे आंसर गड़बड़ हुए हैं.
-2.6 into 10 to -3.
एक्चुअली मैंने ऑनलाइन में गड़बड़ करी है, दैट्स व्हाई.
सर आगे आंसर दोनों कुणाल और मेरे टैली हो रहे हैं सर.
टैली हो रहा है ना, ठीक है, फाइन. आई थिंक नाउ ऑल्सो आई गॉट द आंसर्स करेक्टली. आई थिंक ठीक है. I think you got what exactly has to be done, isn't it? I got these answers. Okay, someone please check. Check the value of u3 with my answer. हाँ सेम है.
सर बराबर आ रहा है.
बराबर है ना. ठीक है. Good. So this is how you have to solve the problem. And in the previous class, I have already explained you how to get the stresses and strain, because the value of u1, u1, u2, u3, u4, v1, v2, v3, v4, they are now already known to you. Only unknowns, that is u3 and v3, u4 and u4, will be known to you. Once you solve this, all you have to do is just substitute the values, and then you can get either the stresses or strain or maybe even the reactions. Okay. So, are there any questions? Otherwise, we will stop then. Sorry, बोलो.
सर जो बाउंड्री कंडीशन है वो केवल केपी तो नहीं लगा सकते क्या केपी निकालने को देना.
नहीं, उनको के ग्लोबल निकालना पड़ेगा, बिकॉज के ग्लोबल में क्या होता है कि उसमें सारे नोड्स का कंट्रीब्यूशन होता है ना. So because of that, you have to first of all generate the global stiffness matrix. Then only you can go for the applying the boundary condition.